Hey guys, I wanted to review for your test, which is waves. It's coming up. We've learned about waves. We learned about the electromagnetic spectrum, the different types of waves. We've learned about how light waves bend by refracting, reflecting, and diffracting. So we're going to talk about a few of those things. So the first thing I want to talk to you about is the Doppler effect. Remember, the Doppler effect is the one to where if an ambulance is coming towards you, that sound is getting louder because your sound waves that look like this are getting compressed together with a higher frequency and sounding louder. And then when they pass you, they rarefact and the frequency goes down. All right, so that's the Doppler effect. Now, compressional and longitudinal waves. Remember, those look like this. These are your sound waves. They move left to right in the same direction, parallel with the direction of motion, because energy is going this way and the wave is going this way. So compressional or longitudinal waves go in the same direction of the energy. So they are in the same direction as the energy. All right, what color of white light has the shortest wavelength? So if we look at your electromagnetic spectrum, your visible light is in the middle. And it says what color has the shortest wavelength. So we know our shorter wavelengths are over here. Shorter wavelengths are on the right hand side. You can see they're really close together. So which color would have the shortest wavelength? Well, if you remember Roy G. Biv, the farthest to the right is the V. So violet would have the shortest wavelength. All right. Solar collectors, what color would they be to absorb the most heat and most light? Remember we talked about white reflects all light, but black objects absorb all light. So you'd want your solar collectors to be black. Okay, so sound waves can help detect how deep parts of the oceans are. So they send a sound wave down to the ocean floor and record how long it takes to return. So we're going to talk about sound in water and in air. Okay, so remember sound travels the fastest through solids, then in water, and then the slowest in air. So the speed of sound in water travels faster than air. All right, so during the Doppler effect, we just talked about waves changing frequency. As the object approaches, the frequency increases. As the object passes, as the object approaches, the frequency increases. As the object passes, the frequency decreases, and it spreads out. So sound waves travel in a higher frequency as it approaches. As soon as it passes you, they decrease to a lower frequency. All right, so we know photons are little particles of light that make up light, so remember that. If we have a thin metal sheet combined with a transparent sheet, which means you can see through it, what could we be using as a transparent sheet? What could something be that you could see through? Well, you can't see through a mirror, you can't see through wax paper, and you can't see through a thin sheet of paper, not perfectly. So the only thing transparent would be glass. All right, electromagnetic waves from the sun differ from sound waves in that electromagnetic waves do not need a medium. They can travel through space. They aren't mechanical because that's sound, but they do not require a medium. Electromagnetic does not require a medium. It can travel through empty space in a vacuum. All right, we want to know the type of wave that has the shortest wavelength, right? Shortest wavelength. So shortest wavelength is going to be on the right-hand side. That would be gamma, okay? A banana is considered opaque, meaning you can't see through it. The only color you see is yellow. That means it reflects yellow. All right, the longer the wavelength, so think long to the left, the less energy we have. You can see that here. If you go to the longest wavelength, which is right here, we have a lot less energy. So if you think about it right here, the longer the wavelength, the less energy that we have. Low, low, and long on the left. All right, we don't even need to worry about a lot of these because think of this. It's asking, we can use this table as evidence for which of the following. Let's just read the statements. Waves transfer energy in this exact same way through all materials. We know that's not true. Waves transfer energy differently. We know that is true. Waves can only transfer energy through solids. That's not true. Waves don't need matter. Not necessarily true. So we know that waves transfer energy differently. And if you looked at this, we'd see gas, liquid, solid, and we'd notice there's different speeds for pretty much all of them. All right. All waves require a medium. Nope. Waves can transfer energy when they interact with matter. Sure. All waves travel compressionally and longitudinally? No. and waves are never affected when they interact with matter. Not true. So it has to be A, that waves transfer energy. Now, if a wave passes under an object, such as a fishing bar, but the object does not move forward, why? Well, the water molecules vibrate perpendicular to the direction of the wave moving up and down. So we know if water waves go like this, they're transverse, they travel like this. So the water waves going up and down, and even though the energy is going left and right. So which arrows would represent a refracted ray of light? I don't see the image here. But what we're going to notice is when it's refracted, it's going to be bent and slow down. So it's going to be the one that is behind. Okay? Now, waves transfer blank from one place to another without transferring blank. Well, we know all waves transfer energy, so it has to be D, without transferring mass. All right, so we want to know the amplitude of a wave and the wavelength of a wave. Okay? So the amplitude is going to be the height. The wavelength is the distance between two waves. All right, so to understand earthquakes, now we know earthquakes travel compressionally and longitudinally. So they did this experiment and they found, just think about an earthquake. So this says waves transfer neither matter nor energy. Not true. Waves transfer both matter and energy. Sometimes. Waves transfer energy, but they don't transfer matter. Or waves transfer matter, but not energy. It's not this one. It's not that one. So it has to be one of these two things. So it says the class created a model village on top of the table. The village included houses. The pounding represented seismic waves. After a short time, many of the plates fell over and some of the pops. But we know that all waves transfer energy, but some of them don't transfer matter. So we're not going to say that they transfer matter. Maybe the shaking caused it to transfer, but the energy itself did not pull the houses with it. So which is an example of compressional or longitudinal? It'd be something with sound wave from a drum. A student makes a speech from the front using the microphone and everyone can hear him. If he made the same speech at the same volume in front of a concert auditorium, would the students in the back likely be able to hear him? What do we think? I would say no, because if he's at the same thing, the intensity of the sound decreases as the distance from the source increases. That means if he's standing in the front now, his sound intensity is not going to be as loud if you're standing in the back as if you were in a classroom. All right, the crest of a wave. The crest of the wave is the top. A wave that travels up and down occurs in the ocean. That's going to be your transverse wave, the ones that look like this, up and down in an ocean. Absorption, when things absorb light. So it says what happens to energy of light absorbed in a filter. Let's imagine you got on a black shirt. When it absorbs light, that changes to heat energy. Okay, so which of the following principles is involved when you see an object such as a plastic straw? We did this in the lab. That's going to be refraction because it's slowing down as it's hitting water. If two flashlights shine on a wall, the spot on the wall becomes brighter. This is due to constructive interference. You have two waves building on each other. The trough, you know, is the bottom part of the wave. In the spectrum, which has a lower frequency, anything to the left is going to have a lower frequency. So if we look to the left, X-rays, gamma rays, UV, microwaves. Microwaves is going to be the farthest left out of those choices. All right, so solid, visible light is the electromagnetic spectrum. Which color has the longest wavelength? So which color is farthest to the left? That's going to be red. Well, red's not a choice. Orange would be next. Longest wavelength. All right, and then we have a few review questions. So solids are going to be things in the periodic table that are to the left of the staircase usually, like a metal, like potassium. Gases are going to be things to the right of the stair step, like your nitrogen. Okay. Elements in the same group or family are similar in that they all have the same number of valence electrons. The oxidation number or the charge, if they have a positive charge, they're called cations because all metals are going to lose one or more to become stable, giving them a positive oxidation number. Last one, the periodic table and the electron dot diagram. Based on the number of valence electrons, what is the correct formula when bonding nitrogen to hydrogen? Nitrogen has a -3 charge. Hydrogen has a +1 charge. So it would be the 1 from hydrogen goes to nitrogen, the 3 from nitrogen goes to hydrogen, NH3. All right, that's it.